There were quite some questions during the break, and I hope there are no more for the moment. Let's go on with the lecture, and the next step is looking at 3D images. So images, what you normally think about is just a 2D thing, a picture or something, but images are actually also higher dimensional. And what we can have is, for example, a volume. So that would be, for example, a tomography. But if you look at a time series of 2D frames, that is a movie, that can also actually be interpreted as a 3-dimensional image. And then you can do some interesting analysis based on that, using the frames along the time in your analysis. Another type of a 3D image is also hyperspectral images, and but I'm showing that as an example soon. So let's see how you can create and look what a 3D image look like in Python. We have here created an image. It's actually just the numbers 0 to 26. And they are reshaped into a 3 by 3 by 3 image. And looking at what it look like, we have then some slice planes in this image. And you can see how they are arranged within these slices. Another way of showing it is as, instead of just as a matrix list, you can also show it as images. But visualizing 3-dimensional information on a 2-dimensional screen gives us some troubles. One way, if you have very few slices, is to do it like this, that you actually do some kind of montage where you place all the slices on the side of each other, and then you can see what they look like. This is an approach that you can use if you just have a few slices that you want to compare. But if you now would have 2K in cube, then you can't do it like this. That would be ridiculous, actually. So for that, you need some kind of volume rendering to do the visual inspection or select single slices out of the data. What you can also have is, if you look at the images, I said before, we just have a scalar, but it could be that you have multiple values on each pixel. One case is actually an RGB image, which has 3 color values for each pixel. But in this example here, we have an intensity and we have a transparency. And for this case, we then would have a table here of the positions and the intensity and the transparency. But that's getting harder also to visualize. So let's see what we can do. One way, if we have 2-dimensional data, is to look at the intensity and transparency individually. Then we can plot them like these blobs here, different values for the intensity and transparency. This is still in a grayscale color map, but we can start playing with the information, and instead we can start using one as intensity and the other one for the shape. And that may make sense in some cases, but that is also from case to case what kind of combination of glyph sizes, glyph colors, and so on that we can work with. It could even be that you have one sets the color map, one sets the intensity, one sets the size, and yet another one sets the shape of this glyph. So the shape could maybe fluctuate between different glyph shapes, and well, then it's up to your imagination how you would combine all these ways of showing different values in the same. Another way, if you, for example, have a vector field it would make sense actually to show this vector field in the form of small arrows or even as streamlines through the data, which is also an alternative way of showing multi-valued pixels. Taking it one step higher is to work with hyperspectral imaging. So in this case, we have a microscope image. And in this, we measure on all these points here that are marked up. We measure even the full light spectrum for each point. And that's pretty much information. And it's used also, for example, in neutron imaging, where you look at the material properties based on the neutron energies. And this is something that I think I'm going to have an example of in, later in the segmentation lecture. So what we have is, in this case, we have X, Y, and then we have on each position, we have a wave number, and we have an intensity value. So that is the information we have in this data set. And that also needs to be presented in some way. One way is actually to look at some few pixels and see what the spectra are looking like. That can also be quickly overwhelming to see what it's actually showing. So you have to come up with some way how to visualize the data for it to make sense, and for on one side, but also in a traditional way that people understand it. Because if you come up with a new fancy way of displaying the data, you probably will get pretty hard critics from the referees when they are looking at your paper. Or you have to explain exactly what you're doing. It could be that you're a forerunner to bring up a new way of showing the data, but be careful when you introduce new visualization techniques. So now we have talked about a little bit about the images that we can come up with. And next thing is, where do the images come from? And a typical image formation system is that you have some different basic components here. You have the excitation. So you have some kind of source bringing lights, impulses, something that you want to let propagate through or bounce off the sample. Then you have your sample. I like ducks. And from when the excitation goes through the sample, you get some kind of response from it. It could be attenuation, it could be scattering, something. And this response signal will be captured by your detector. And this gives the whole chain. In some case, well, the detector actually also contains some optics and the electronics and some converters. So it's a little bit more complicated than just saying detector. And there are very many sources of these images. You can talk about microscopy in different ways, using different excitations, phase contrast, looking at how waves are propagating through the sample. You can also have atomic force microscopy, where you have actually some kind of probe that's actually sensing on the sample. So there are very many ways of getting the images. In the end, what is important is you get something that is some values on a grid producing these images. So the typical traditional direct imaging is that you have some kind of sample going through, the light source is going through or is reflected from the sample. So you have this original sample, and then you do the measurement. When it goes through your acquisition system, you maybe get something that is blurred, it's rotated, and that requires you to do some kind of reconstruction step maybe afterwards to get what you really want. In this case, it was a deconvolution and also rotation to get to what you want. That depends on the technique. So this is the typical steps that you can have. Sometimes you don't have to do some kind of reconstruction to get there, but you never know. Then you have the indirect computational image. And then you actually record the information that does not really, or may not really resemble the object itself. But in order to get the image you want to see, you need to transform it somehow with the computer to produce the image you want to see. And that could be, for example, you do measurements in the frequency domain, you get a spectrum like this, and only after you have transformed it into to real space, you can see what the actual object is. From this one, you can hardly see what it should be. Very simple structures. With some experience, you can start recognizing, like just disks or squares. You would recognize faintly what it is in the spectrum, but a complex structure like this one is very hard to recognize through the spectrum. So you really need to do the transform to get to real space. In the traditional image, we have our light source, which goes through the lens, and then it's actually shown on an image plane. And that is actually what we are acquiring with the detector. The image plane can be a scintillator, it can be just a camera directly, depends. It can also be if it's a transmission. So I get a question here on the chat about projections you have in tomography. Yes, tomography is an indirect method because the projections, of course, you can see the sample itself, but in order to see the slices in 3D, you need to put it through the reconstruction, which transforms it from the acquisition space, which is in angles and projections, into a three-dimensional volume. So yes, you need to compute. That is an indirect method. You can't see three-dimensional data without a reconstruction. Making the whole model a little bit more complicated, we have a lot of contributions here. You have the image, the beam profile. So the beam itself is maybe not perfectly flat. Then you have the sample absorption, and those two are convolved, no, multiplied. Then you convolve it by some kind of propagation function. And again, multiply by some optical transfer function, and again, multiplying by the detector. I didn't hear that. Sorry, can you repeat it? Okay, can you write it in the chat instead, please? So, and on top of that, we also have maybe some dark field contribution. So it's just a bias from the detector, and all of it is then this final signal that we get. So it's a pretty complicated system that we're going through. And then if you go multispectral, you will even add the wavelength of this light source. So then you have even more complicated situation to look at. Some examples is here. Actually, here comes the tomography. You can also work with microlenses doing light field tomography and photography, and computationally you can actually play with the depth of field in depth of focus afterwards, just based on the information you have provided from these micro lenses. Another thing would be also to work with diffraction patterns or with the hyperspectral imaging, and also atomic force microscope. So different things, they need to be converted in order to be able to work with it as images. Then it depends on how to work with the data now that we got these images. There are different ways of looking at the analysis. In principle, what we are talking about is a bucket of pixels. So more or less values spread distributed over the some kind of limited array. And now you have to put this one into some useful information. I mean, the images may be nice to look at, but they are not really analyzed in the sense that you may need it for your research project. And the first way is to look at it as the experimentalist. So then you look based on the problem you have, you do a top-down analysis, and often the analysis is also based on physical, real models in what you observe. So examples would be counting cells, looking at porosity, and this is one way of doing it. And the other way would be, if you have the background in computer vision, then you may look at the problem a little bit differently. You look at the methods that you have in your toolbox, and you look at specific features in the image, and also the model you're working on is more based on signal processing concepts. So it would be if you're looking at edges or looking for features. And also typically in computer vision, you try to test your approach working with features that you have engineered, or actually you produce actually test image to see how the data is or how the methods are working with the data. Then we come to the deep learning approach or data science approach. It's mostly results driven. The analysis concept is biology inspired. So it's kind of looking into how the brain is working when it tries to recognize things. And then we often start building the image processing and analysis from scratch, in the sense that you're not using the traditional ways, but you're actually looking at new concept for how image information is perceived. Important is, for example, that you need to tell these methods or often need to tell these methods what to look for. That's why it's called result driven. So you have to have some training data in order to do the analysis. So example of this would be captioning images. So telling this is a monkey, this is a cat, this is a dog, this is a number, this is a traffic sign, whatever. Another thing it can also be used for is identifying unusual events. So kind of anomaly detection within the large data. So switching over to a little bit more, call it science theory. So first of all, what is the purpose of doing science? In principle, what we are up to is to discover and validate new knowledge. And it's important, this validate is a very important thing, because you can always discover something, but if you can't check that it's really what you think it is, then there is no point. So we have to use these scientific methods that we have in our toolboxes as an approach to convince the people that you actually are seeing what you are claiming. Of course, we should build the results upon what other people have done and don't start from the beginning. So it's always important to have a background review on work already done. A couple of things that you have to think about is that quality assessments, of course, they are important. That's what you do when you see an image, look at it, okay, that makes sense, or I have about this going on. But a qualitative approach is very difficult to reproduce and scale up to large amounts of data. The quantitative analysis, well, it may not be perfect, but at least it provides metrics from the data which can compared and important also regenerated by anyone else. In the qualitative analysis, it's very much depending on what you think is right or wrong. So if someone else has a different opinion, that person would probably find something completely different from the data, or maybe not completely different, but different at least. And then you have to argue about your conclusions. But if you have something where you can put a metric on it in the quantitative analysis, then of course you can show that you have this measurement with that error bar. It's a clear case, hopefully. When we mix the science method with imaging, the first thing is it's very easy for the human eye and the human brain to see, well, something is going on. We can also quickly make an assessment, not even programming, saying, okay, this is going on, that is going on. And the problem is when we want to take the step over to doing a quantitative analysis, it's very difficult with images. It's sometimes very frustrating even, because it's so obvious when you look at it on the screen. But telling the computer how to do it, it's something completely different. If you, for example, would measure the temperature, it's very easy. You just take a thermometer and you can see it. Okay, 50 Kelvin, you're done. Maybe you can add some error bars on it, but in principle, that's easy. But doing image analysis, there are so many factors that you have to take care of in order to find your analysis that is reliable and not confusing you even more. There are a lot of tools out there, open source, commercial, algorithms. There are even several journals about image processing algorithms. So it's an active area of research. The question is only to find what you need. And typically you need a multi-step approach to get these right analysis. And as we have a lot of data, the experimenting, getting the right recipe to do it, that can be very time consuming. So very important is, before you start anything, is to ask yourself some important questions. First of all, you have to define how you want to use your images, not just doing the experiment, but first, what is the purpose of producing images? And nice renderings like this little gold piece here, they may look very beautiful, but they don't help you much in your science case. They're nice to have in the presentation, I don't say that, and you probably should have them because that's an eye catcher. But what you really want to do is producing information like this, where you can say that different parts of this histogram correspond to different components in the sample. So this was the analysis of a rusty nail, and we can see that there is some soil on it, some soil and corrosion, uncorroded iron, decreasing corrosion, and corroded parts. So you have very different informations in this plot, and this kind of plots is what you are asking for in the end. And the first questions you have to ask before you, now you have defined what you want your image for, the first thing is, of course, what am I looking for in these samples? Is my original question specific or too general? You have to have very clear questions when you start doing your analysis. Otherwise, you will end up in a very confusing and frustrating workflow to find anything in your data. And the analysis actually starts before you even start doing it, because you have to plan the experiment in a way that you can make the analysis easier. Maybe you have to do one step extra, or you have to do some extra documentation, but everything you do during sample preparation and experiment itself and has an impact on how you do the analysis afterwards. Sometimes your original question, it's not even related to images at all. So you need to translate this into the vocabulary of image analysis. Otherwise, it will be hard to anyway define a workflow. And the last thing is also to provide as much a priori information about the sample before you go into the analysis. And then, of course, you have to check how you can use this information in your analysis also. So typical things you want to do is compare treatments, understand and model processes, or even just plain and simple inspect components, see if there are cracks. And also what you want to do is maybe some 3D visualization still, sample characterization, process modeling. And the question is what we actually can measure in the images. We can, based on the gray values, we can define material composition. We can also look at material transport within the sample. If we go for the shapes that you see in the images, it could be looking at these cells that we saw in the bone before. We can identify these items and count them. We can also measure the volume or size. You can characterize the shape in different, is it elongated, is it roundish, is it complicated or something like that. So these are things we can put numbers on. And now is the question how you can bring what you want to do, for example, compare treatments, into the kind of measurements you can do from the images. So looking at how do we quantify things, and the first thing related to what I said, the human eye can see a lot, but it can also be tricked. For example, the classic illusion is which one of these squares is the brighter one. And many would, with a quick view, just say this one is the brightest. But in reality, they are actually the same intensity. But you're tricked depending on the context you see this object in. Another thing is if you look at intensity gradients, a classic problem is that you see some kind of brighter bands, bright darker bands around the transitions between these bars. And that's also a problem with the eye, that the eye somehow has some kind of edge enhancement built in, because these steps, they are actually constant. I didn't do any tricksing around to get these. So this is something that your eye is actually tricking you to think that it sees. Now you have defined all your questions and hopefully also got some answers to them. And now you want to select the right tool to do your processing. And you have some basic criteria to look at. So for example, how many samples do you have? How complex is it? Is human interpretation and interaction needed at all? If not, the better. What is the end product? How are you going to use the information you extract from the data? And are there already methods and tools available to do this task? Of course, then you're in a safe ground. So then you can just plug the data into it. And also, will there be more similar data sets, and how many? And based on these criteria and answers on these criteria, you can do a choice between maybe working with interactive tools. That would be a lot of human interaction. Then you could go for some scripting using existing toolboxes, which is what we are mainly going to do in this course. And finally, if these toolboxes doesn't provide you what you want, then you have to go for developing new algorithms. But just keep in mind, XKCD, they made this nice cartoon here telling about how things are going on when you do try to write your own code. So be careful not to too hastily go into too large analysis, writing too large analysis workflows. Do it really with a good judgment in order to not ending up in ongoing development and no time for doing what you actually should do. That I have seen and done even myself several times. Now we got some code and first experiments and some code, and there are different terms about what is needed in a scientific project. So we can talk about reproducibility and repeatability. And reproducibility is something where you have made some observation, reported about it, and someone else wants to do the same thing. And if an experiment is reproducible, then the experiment that was reported should provide the same results as the one that you try to do to replicate it. And that would be the whole way. We have the experiment going on, some analysis, and the output. Then someone else sets up the exact same, or as they interpreted the same experiment, and then do some analysis, what they think is needed, and that should show the same result. Repeatability is a more relaxed concept, because then you have some data. Actually, two persons are going to use the same experiment data and the same analysis workflow, but they are different persons doing it. And that should produce the same results. It's more relaxed, but still it can be hard, in particular if you have interactive parts in the project. So what science demands, it at least that you can show that you have a repeatability in your analysis, but ideally it should be reproducibility that you should have. But sometimes, or mostly, it's very hard to achieve this. I mean, experiment conditions can change very rapidly, and that can make it hard to actually reproduce the exact same conditions. And if you do animal and human studies, it's very time consuming and also expensive to reproduce. So therefore, there are a lot of databases providing data that you can use in your studies instead. And of course, it's that the fact that you have terabytes of data doesn't make it easy to work with, and also not pass around between different groups. And sometimes it can also be, particularly if you are working with the medical data, privacy can also limit the sharing and the access to the data. So as soon as you have people involved, or maybe also company secrets involved, you cannot share the data anymore. You can possibly publish it, but you can't share the data for someone else to play with it. So science is difficult to get your answers, of course, but the whole thing that you have images is a thing that makes it very much more complicated. I've seen projects where people write a fantastic project and then with 2 lines they say, and it should be analyzed from the images. In the end, the poor guy is sitting doing image processing for the whole time. Image processing is a multi-step task, and you have very many parameters to play with. And there are also maybe different tools that you work, and it's a very time-consuming task. So in the end, what you should have is at least repeatability. And to improve the possibility to guarantee this repeatability, we should make the data or the whole workflow available so someone independently, third party, could do the same analysis. First step is a good documentation of the analysis step you do, but also writing clear and understandable code. The clearer the code is, the easier it is for someone else to follow. It's even said in software engineering, a good software engineer is the one who writes code that can make himself replaceable. So that would be kind of a goal when you write the code. The last thing I'm going to talk about today is different workflows for doing image analysis. And as I already mentioned, it is a multi-step task. So that's something that can hopefully, that will be done with computers. And let's start with the side of how the computing is helping us. And one thing is that computers, or CPUs, they get larger with more transistors. And that follows the so-called Moore's law, which says that the number of transistors double every 18 months. And that's something that actually went on and still, I think, went on. This plot is only till 2010, but I think it's still going that way. But what you can notice is that the clock speed has stagnated around 3-4 gigahertz, and that's where it will stop, because that's a physical limitation. Still, we get faster computers all the time, so something is happening. And what is happening is actually we get multiple cores in each CPU, and you may even have multiple CPUs on each motherboard. On top of that, we also have new modalities like graphic cards, which can be used for computations instead of doing graphics. And that's something that has been used a lot in the machine learning and image processing communities. So the conclusion from this is that we need to have parallel code in order to process things efficiently. Otherwise, you will be stuck on a single core, and that's not very fast. Another thing that has changed is cloud computing. And that's a concept that has been growing up with data science development. And computers, servers, workstations, they're actually wildly underused. Most of them actually use less than 50% of the time they are available. So buying a big computer that sits idle most of the time is really a big waste of money. And that is what these cloud services are about. So they provide buy-in time where you can buy in for the time you need the CPU. Maybe it costs, for the moment, maybe cost a little bit, but in the end, it is a lot cheaper to buy in some time on one of these services. So they are different. So Microsoft Azure, Colab, Amazon Web Services, and it's actually not that high of a cost for smaller things. And for example, a PhD student in Switzerland is about 400 times more expensive per hour than an Amazon machine from the web services. And the prices, they are kept pretty low because there are many competitors on this market, and that also offers you flexibility. You can say you want this and that kind of computers, so many, and they should be equipped with graphic cards, etc., etc. So you have very big flexibility in how you configure these services. Now let's do a little toy example in the workflow analysis. Let's make a soup. So when you do a soup, the first you do is you buy the vegetables on the market. Then you go to the butcher and buy some meat, and then you go and chop the carrots, chop the potatoes. You start heating the water, wait until it's boiling, and then you add your chopped vegetables, and then you wait another 5 minutes, and then you add the meat. So that's pretty simple, and you see a clear workflow. So you have a recipe how you should do stuff. If you do, oh, this one turned out strange. If you do a little bit more complicated, I think I have to change something here. Why isn't it working? Okay. Strange. Okay, anyway, in this workflow, you try to identify, okay, some things you can do in parallel. So you can like put on the water when you go to the market. You can go, you can fry the meat while you're boiling some veggies. So that gives you some flexibility in how you can do things in parallel. Sometimes you can even improve it even further. So in the computer, this would look something like you make a flow chart like this, where you can see here that it goes from task to task going on. And the complicated soup, then you can see that there are two parallel workflows. So you can buy vegetables, you can heat the water, and you can buy meat. Those are individual tasks that you can play with. And you could actually even delegate it, having 3 people working on this, and in the end produce a soup faster than if you do the sequential approach. That was the first one. And this also has a name. It's called directed acyclical graphs. And in principle, if you're good at it, you can represent almost any computation without loops using these DAGs. And it's also possible to break down the computation into pieces, which then can be distributed. Like in the soup, you could have 3 people working on it, and then in the end, you will merge it. And there are a lot of tools doing this. Different frameworks. So one is PyData Dask. There is Apache Spark, KNIME, TensorFlow, PyTorch, and so on. There are many of these packages for machine learning, large-scale computing. They have implemented this Dask concept, DAG concept in their workflow. So let's look at a little DAG that we are creating. Here in this example, I'm creating 2 little variables, one with zeros and one with ones. I'm only showing one here. You can see that here's the variable and it's 1 piece. Now, if I want to add these 2, I would write it just like this. So image 3 is same as image 1 plus image 2. And if we look at this, we can see that the variable for ones is coming into an adding operation, and then the result is coming out here. You can see there are 2 images and 2 image blocks, and in the end we have 1 image block. Oops. Yeah. Okay, I didn't define it on the previous slide. Nah. Okay, it's not meant to be. Okay. Let's go on to the next one. Here we have a little bit more complicated operation. We want to show image 1 minus 10 and image 2 times 50, and then we add them. Then we see, again, we have two workflows here. One that is doing the subtraction, one is doing the multiplication, and not until we come to the adding, they have to join forces and show their results. So that would be kind of a barrier where everything needs to be synchronized. And then we can go big. If we have a big image, maybe it's not so easy just to split out the different branches of the task, but you can also split the data itself. And here we have an image which has a size of 1K by 1K. And this image is divided into chunks of 512 by 512. That means we will have one variable will actually be split up in several pieces here. And you can see here that one piece is the corner, the one is the other corner, that's the lower corner, that's the other lower corner. So we actually split up it into 4 blocks that are processed. And when we continue now doing the same operation we did before, we see that this workflow is repeated 4 times. And this means there is an opportunity to dispatch this into the different CPUs or machines in your cloud or on your single machine. So this is where you can start seeing the parallel possibilities in this processing. Now doing a matrix multiplication is a little bit tricky because it actually needs the information from all elements, and that's why you can see that the graph is getting pretty complicated because it needs information from each one of the others. Let's see. Yeah. In order to compute the final result. And then in the end, we end up again with 4 images or sub-blocks like this. So a little bit more complicated, then we mess it up a bit. Then we do a mix of a matrix multiplication and element-wise multiplication. And you can see that in the beginning, we have this synchronizing part where the matrix multiplication needs to be talking to all the elements. And then it splits up into yet another set of parallel workflows. So this is also something that can be used in this large frame computing. But you have to see that there are some synchronizing points where you have to stop a little bit until you get the results. And then you can go back into the parallel workflow again. Now getting really complicated is doing convolution, but you can still do it. The problem with the convolution is that in order to do it without boundary effect, you need to have some overlap between the different chunks. And that is what you see here, that it actually extracts a little bit around, like an extra frame around the image. And that needs to be added. And finally, you can get the convolution done. And then you can trim it down again into the right size, and then you get to the result that you want to have. But now this is a pretty complicated, large workflow. And usually you probably wouldn't even look at the full workflow like this when it gets too complicated. But it shows you that you can actually do a lot of operations by describing it in this DAG framework. And that is actually what's helping you if you would like to do processing on large scale computers. Another reason to do this is deep learning, because as you can see here from this graph about deep learning from neural network, you have some input nodes, and these nodes are multiplied by weights, and then there is some kind of activation. And in the end, everything brings back into some output signal. This is nothing I'm going to talk very much about today, but anyway, you can see that these graphs, they can actually be very well represented in the DAGs. So that's also a reason why they will be important for maybe some of your projects. And with that, I actually reached the end of the day, and it's 11 o'clock. So today we have been talking about the images, how to work with them, how to work in a scientific framework. And now at the end, I ended up talking about frameworks and how to handle large data amounts in a parallel framework. Next week, I'm going to talk about noise, filters, and filter evaluation. And that is something that is a very important first step when you start processing images. So with that, I thank you for today, and let's see you at the exercises. I think I just leave the channel open. So if you have questions and so on, just go ahead. Thank you.